Let us talk about reverse a linked list problem. We are given a linked list. We need to reverse it. For example, if we are given this linked list, we are basically given head of this linked list. We are given head of this linked list. This is our head, having a pointer or reference to this node. And once we reverse, this should become our new head. The 40 should become our new head. And if you notice, 40, which was the last node, now becomes the first node. Then 30, second last node becomes the second node. Third last node becomes the second node. And the first node becomes the last node. Let's now see this second linked list. We have given this head and we want to change this to 30, 20, 10. And this is our modified head. Now let's talk about the third linked list. We are given a linked list with single node. So we are mainly given this head. And once we reverse it, we keep the head as it is because there is single node, so there won't be any change in the linked list. Now let's see this final example. We are given an empty linked list, capital null in C++ and small null in Java. So once we reverse it, we keep it null. Now please pause this video and think of an approach that takes head of the linked list as argument, reverses the linked list and returns the new head of this linked list. Let us first quickly talk about naive solution to solve this problem. The idea is to use an auxiliary array. We create an auxiliary array. We copy the content of the linked list into this auxiliary array. Then we traverse this linked list again and we copy the contents of this auxiliary array back into the linked list in reverse order. So we copy 30 first, then we copy 20, then we copy 10. So we get the reverse linked list. Now to create an auxiliary array, we use vector in C++ and array list in Java because we do not need to know the size of linked list, right? We do not want to traverse unnecessarily extra linked list to know the size. Vector and array list are dynamic size arrays, so we can add as many elements as we want. So we create a vector in C++ and array list in Java. Now we traverse this linked list and we add every individual item of this linked list at the end of array list and at the end of vector in C++. Now we traverse this linked list again, and what we do this time, we copy the last item of vector or last item of array list into the current node, and then we remove the last item, right? So this can be done in one line in Java, and we have written 2 lines here in C++. We first get the last item, then we remove the last item, right? So this is how we get the reverse linked list. Now if you take a look at this code and implementation, we are traversing the linked list twice. We are using auxiliary space, and this data here in example is an integer data, but this could be a huge data, maybe an object which is stored in the linked list, and copying it could be a costly operation. So this is not an efficient solution. First of all, it requires 2 traversals of the linked list, requires extra space, auxiliary space, which is big O of n. Now, please pause this video and think of a solution that traverses the linked list exactly once, does not require any extra array or something. It requires only constant extra space and reverses the linked list. Let us now talk about the efficient solution. The idea is to change the links rather than changing the data. And this way, we reverse the linked list in one traversal. We do not need to change the data. We just need to change the links. Now, how do we change the links? We begin from this node. We one by one traverse all the nodes and then reverse the links. So when we are at xith node, we must have reversed all the links from x1 to xi-1. Our linked list should have become this, and we are here at xith node, and we must have stored the reference or pointer to xi-1 so that we can change current next to this particular xi-1th node, right? So we are here, we have reversed this part. Now what changes we make in this linked list so that this link is reversed? See, one thing is very clear. We need to make previous as currents next. But should we immediately make the previous as current next, or should we be doing something more? If I simply do current next equal to previous, I lose track of this linked list, right? So I need to store the next of current first, and then I need to make currents next equal to previous. So the first thing that we do is we store next of current so that we do not lose remaining linked list when we are changing currents next, right? If we change first currents next and we do not store it, we lose the track of this linked list, right? So we store it in a next reference or pointer, right? So we store it in a next variable. And after that, we change this link that we were supposed to change. This was our main task, right? So we need to change this link. So we change this link to this side. Current next equal to previous. That's what we do in the next line. And once we have done that, we need to set previous and current for next iteration, right? Because in the next iteration, this should be your current and this should be your previous. For that purpose, we do previous equal to current and current equal to next. And this order is also important. If you do current equal to next, then you will lose the track of current node, right? So you need to first copy the current into the previous, then next into the current. Right? That is how we process a particular node while we are reversing the linked list. So that's how we processed this node, right? And after we have processed this node, our previous and current are going to change. We are going to set the previous here and we are going to set the current here. So that next iteration, when it begins, it also does this way. So the idea is simple. We are going to traverse through the linked list using a current pointer or reference, and then we are going to do these operations for every node. Now please pause this video again and try to write down complete function that reverses the linked list and returns the head. One last thing that you must notice is what should be your new head. When you have reversed the whole linked list, say everything is reversed and this is also reversed. So when you are reversing this particular node, you need to stop after this node, right? So how will you stop? You will say current equal to current dot next or current arrow next, and current becomes null. So you have null after it and your current refers to or points to this null. So you need to stop here. But you need to mark this node as head. So how will you get hold of this node? This node you can get by using previous. So you will say previous is your new head. That is what you will do once you have reversed the whole list. Once your current becomes null, you will say this is our new head. Previous is our new head. This is how this iterative function works. I think you can now write the complete function quickly. Let's now talk about the complete function. This function reverses the linked list and returns the new head of this linked list. And how does this function work? Initializes the current as head, initialize the previous as null, then runs a loop while current is not equal to null. And inside this loop, it does these steps that we just discussed. And once it comes out of the loop, it comes out of the loop when current becomes null. So when current becomes null, your previous must be head of the reversed linked list. So it returns previous as new head. Let's see the working of this code one by one. So initially we have this thing. We have current as at the head. We have previous as null. Right? That's what we have at initial stage. Now we begin with the first iteration. And inside this first iteration, what are we going to do? We are going to first store the next as current arrow next or current dot next. So our next becomes this. Now what are we going to do? We are going to do current next equal to previous. So we change this link from here to here. So current next becomes null. And after that we change previous. So we make previous equal to current. So previous was earlier null. Now it becomes current. And after that we make current equal to next. So current which was earlier here now comes to here. Right? That's what we get after the first iteration. And this is what we are going to get after the second iteration by following the same steps. We'll change next to current next. So next will come here. Then we'll change currents next. Currents next will now become previous, which is 10. And then we'll make previous equal to current. So previous will come here and current equal to next. So current will come here. So this is what we will get after the second iteration. Now we do the third iteration, and inside this third iteration, we again repeat the steps. So we make next equal to current next. So our next becomes null. We make current next equal to previous. So current next becomes 20, right? This node becomes, now its next was earlier null, now it becomes 20. And now we change previous and current for the next iteration. So previous now becomes 30 and current now becomes same as next, which is null. So when we begin this next iteration here, what happens? We do not go inside this iteration because current has now become null. So current now becomes null, we come out of the loop, and you can notice that previous is now having head of your reverse linked list. So we return the previous as new head. Let us now talk about time complexity of the solution. Time complexity of the solution is clearly big O of n, where n is the number of nodes in the linked list. We are traversing through all the nodes one by one, and auxiliary space required by the solution is big O of 1.